Hey guys, welcome to another A-Level Further Maths revision video. Today we're doing some more Copio and we're taking a look at polar coordinates. So let's jump straight into this using the textbook. So exercise 5C here. We have a pretty standard kind of question. We've been given the area that's enclosed by the curve. So we're just asked to find the value of A here in this equation. So R is equal to A plus 5 sine theta. And we're told this restriction here that A must be greater than 5. Okay, so we'll probably need that at some point later on. And we know the area is 187 pi divided by 2. So, when you're doing a polar coordinates question, when you see the word area, straight away be thinking about integration, okay? So, we need to integrate. And the reason we need to integrate is because the area here, so this is a standard formula, and it is given in your formula book. So it's equal to a half times the integral here between 0 and 2 pi, because it's a single loop, of r squared d theta. Okay, so r is this equation here, so we're going to square this. So this is a half times this integral of r squared, so that's a plus 5 sine theta squared d theta, and if you expand this here, what would we get? So sorry, it should be between 0 and 2 pi, and again 0 and 2 pi. So what's r squared? So that's going to be a times a, so I'm going to get a squared. I'm going to have a times 5 sine, and then another lot of a times 5 sine. So in total I've got 10a sine theta. I mean, if you find it easy, you can just write two of the brackets out just to see the multiplication a bit easier. And then finally 5 sine theta times 5 sine theta. So we're going to get 25 sine squared theta d theta. Okay, so now we've got this expression squared. At this point here now, we need to start simplifying and then perform the integration. So when I say simplifying, often with polar coordinates questions, because we're using the relation here of x and y being in terms of r cos and r sine, it's often easier to use trig identities. So in this case, this is a half times the integral 0 to 2 pi of a squared plus 10a sine theta. This sine squared theta here, we can use the identity 1 minus cos 2 theta. So what I've got here is a squared 10a sine theta plus 25. Now obviously because this is 1 minus cos 2 theta, we need to pull the 2 out here at the beginning like this. We're dividing it by 2. This is 1 minus cos 2 theta d theta. And now this is a lot easier to integrate. So do it up here at the top. What's this going to give us? Well, we've still got a half at the beginning. So it's a half of, so what we're doing now is we're integrating this with respect to theta, so a squared integrated with respect to theta, that'd be a squared theta. 10a sine theta, so if you integrate that, well, what would you differentiate to get sine? You differentiate cos, you get minus sine, so this has to be minus cos here, so it's minus 10a cos theta, like so. This is quite a long amount without room. So expanding across here, so 25 over 2 times 1, and then integrate that with respect to theta, so that'd be 25 over 2 theta. And then finally, 25 over 2 times minus cos 2 theta, so integrate the cos 2 theta, and you get minus sine 2 theta over 4, and then times it by 25 over 2. So what we get is minus 25 sine 2 theta divided by 4. So this is really messy, it's kind of all over the place. So for now I'm just going to rub this out just so we can see a bit better. Okay, just to get rid of some of this in the way. So now, this is between our limits, so 0 and 2 pi, like so. So all we've got to do now is sub limits in. So subbing the limits in here. So when you actually sub these limits in of 2 pi, essentially what actually happens is you just get left with, so you sub it in where theta is, so you get a squared times 2 pi, obviously don't forget the half in front, so this is a half, times a squared 2 pi. The cos theta and the sine 2 theta here, they just cancel when you sub this limit of 2 pi in and the 0, okay? So essentially all I'm actually getting left with here is 2 pi for a squared theta here, so a squared 2 pi, and then at this point here, okay? So I just get plus 25 pi. Sorry, 25 theta, I can't speak. No, 25 pi, what am I like? 25 pi, okay. There we go. Okay, so you should get that when you sub your limits in. And then at this stage here, what we know is that this is the area, and we're told that the area is equal to 187 pi over 2. So if I just make this look a bit neater. Okay, like so. And we know this is equal to 187 pi over 2. So at this stage now, we just solve this in terms of a. So you can times through both sides by 2 to get rid of the denominators here. Plus 25 pi. And this is equal to 187 pi. Here now, I can divide both sides by pi. Therefore, 2a squared plus 25 is equal to 187. Subtract 25 off both sides. 162. Divide both sides by 2. Let's get a squared is equal to 81. And then therefore, a must be the square root of 81. So normally we'd have plus 9 and minus 9. But again, like we mentioned at the start, a is greater than 5. So a must just be the positive solution, giving us a equals 9 as a is greater than 5. Okay. So there we have it. That's the final value there for a. Next question here. Again, being confident with your trig will get you a long way with these style of questions. So what we want to do is just obtain a Cartesian equation for the curve with these given polar equations. So a told r squared is sec 2 theta. Okay. So what I can do is I can rewrite this. This is r squared is equal to 1 over cos 2 theta. And again, we can use identities here. So we can write this as 1 over cos squared theta minus sine squared theta. Like so. So using this now, we can write this as r squared times this expression here. Because don't forget, r squared is just equal to 1 over this, so times in both sides by cos squared theta minus sine squared theta. That's equal to 1. If I expand this left-hand side now, I'm going to get r squared cos squared theta minus r squared sine squared theta. This is equal to 1. And if we use the fact that x is equal to r cos theta and y is equal to r sine theta, it becomes a lot easier to see now what's actually going on. Okay, so if you square this here, so r cos theta squared, you'd get r squared cos squared theta. So that is essentially x squared there. This r squared sine squared theta, if you square that here, you'd get r squared sine squared theta, which is just y squared. So this is x squared minus y squared is equal to 1. And then you can just write this in whichever way you want. You could give your answer like that. It's technically a Cartesian equation. If I put it in terms of y squared though, y squared is equal to x squared minus 1. And you could write that as y equals the square root of x squared minus 1 if you want. Completely up to you. But that's part A. So let's take a look at part B here. Again, it should be a pretty similar argument. So part B, cosec 2 theta this time. So cosec 2 theta. And again, being confident with your trig identities will get you far with these style questions. So rewriting this, so r squared is equal to 1 over sine 2 theta this time. Okay, so straight away, again like we did with the last one, I'm going to times through by sine 2 theta. So r squared sine 2 theta is equal to 1. So now we just need to apply some identities again. So this time using double angle formula, so sine 2 theta, that's equal to 2 sine theta cos theta. Okay, so applying that here, what we've got then is r squared times 2 sine theta cos theta. And this is equal to 1. Now again, using that relationship, so x is equal to r cos theta and y is r sine theta. Okay, well let's just do a little bit of rearranging here. It should hopefully be a bit easier to see. We could technically write this as 2 lots of r sine theta, r cos theta, like so, which is equal to 1. And then obviously if you've got r sine theta times r cos theta, that's just the same as xy here. So what we get is 2xy is equal to 1. So therefore y would just be 1 divided by 2x there. Okay, so that brings us to the end of that question. These next 2 questions now are again pretty standard exam type questions. So this is taken from one of the old exam questions from the old exam board, also the old exam specification. So question 2 here, you're given a polar equation, r equals 1 plus 2 cos theta, and we're told theta lies between this restriction here of 0 and pi over 2. So we're given the bit of information. We know at the point P on C, the tangent is parallel to the initial line, so that's quite important. So the reason that's important is because if the tangent to C is parallel to the initial line, then we can use y equals r sine theta. Okay, so why are we using y equals r sine theta? Well, it's because we're told that it's parallel. Okay, if it was perpendicular, we'd be using x equals r cos theta, which you will see in the next question. So parallel, so we use this equation, and what we're going to do here, or what we also know, is that dy by d theta is equal to 0. Okay, so using this and using our r, what we can do is we can obtain the differential here, set it equal to 0, solve, and then we've got basically the answer. So putting all that together rather than just saying it, what we've got then is y equals r sine theta. So what we've actually got here is r, which is 1 plus 2 cos theta times sine theta. Just putting our equation together here, r sine theta, where r is 1 plus 2 cos theta. Okay, putting that together now, what we do know is that this differentiate is equal to 0, so if we can differentiate it, will make life much easier. So if you differentiate this, what would we get? So dy by d theta, what's that going to give us? So that's just simply going to give us, so 1 times sine theta, so that'd be sine theta, differentiate that, you get cos theta. You get cos theta, and then 2 sine theta cos theta. You know, we could write that using identities here. What I would write that as is 2. Sorry, I mean my plus sign, what we're doing. Get rid of that. So we can write this as plus 2 cos 2 theta. Okay, just differentiating that. So here now, now we need to use identities to manipulate this, because what we want here is essentially a quadratic. Okay, so that's the idea here. We want a quadratic. So how do I get that quadratic? Well, I get that quadratic using my identity for cos 2 theta. Okay. Now don't forget, for cos 2 theta there's multiple identities you can use, but because we want a quadratic, the one that I'm going to use here is 2 cos squared theta minus 1. Okay. Use that identity there, then we're going to obtain the quadratic that we require. So if I sub that in, what I've got is cos theta plus 2 lots of this like so, and this is equal to 0, okay, because dy by theta, like we mentioned, is 0. So if you expand this, it's before cos squared theta minus 2 plus cos theta. So if we do that up here, what I've got is 4 cos squared theta plus cos theta minus 2 equals 0. Now more often than not, you will just have to use a quadratic formula here just to solve this. So what we're solving here is for cos theta, this is equal to minus 1 plus or minus the square root of 1 minus 4 times 4 times minus 2, all divided by 2a here, divided by 2 times 4, which is 8. Simplifying here, so I just jumped to the straight to the last line of working. We can also omit the negative solution because we're working between 0 and pi over 2, so we only want the positive solution here, so it's minus 1 plus root 33 like so, divided by 8. Okay, now we're told always the pole, we just want the exact length of the line OP, so in other words, OP is just simply R. Okay, so R like we've got in the question, but all we've got to do here now is use what we've worked out for cos theta, which is this here. So we substitute this back into R, like I said before, we're done with the question. So therefore, R is equal to 1 plus 2 lots of this like so, and all we're going to do now is just simplify here. So that's 2 divided by 8, so I'm going to get 1 over 4, so I can write that as 1 plus minus 1 plus root 33 over 4, like so. If I was to times through by 4 now, this would be 4 plus minus 1, well, minus 1 plus root 33 over, well, the 4's gone, so I'm not making much sense here, so let's try and rewrite this. So if you simplify here, times through by the 4, and then simplify, so that'd be 4 over 4, and then if you do all that, what you get is this over a common denominator. Over 4 like that. Okay, and that's the exact length because we've got it in terms of surds and such. Therefore, the exact length and there we have it. Okay, so that's 7 marks for that. Like I see, there's quite a lot of work, and that's kind of the issue with these polar coordinates questions and polar equations. There can be quite a lot of work in it, and it's very easy to make a mistake. But make sure you're confident with your trig identities, trig expressions. So let's take a look at this very last question here. Again, pretty similar, this time from the textbook. So we've got R equals A times 1 plus tan theta. So this time we're told the tangent is perpendicular to the initial line. So because it's perpendicular, this time we're working with x equals r cos theta. Okay, so what we also know is that dx by d theta, I'm losing my voice as well, this is equal to 0. Okay, so let's see if we can make it. So what I can do then is I can rewrite r here and using x. So how is that going to look? Well, what I can write this as is cos, because this is cos theta times r. So this is cos theta times a lots of 1 plus tan theta. Now if you were to consider multiplying through by the cos theta here, I'd get cos theta times 1, and I'd get cos theta times tan theta, but remember we can write tan theta as sin theta over cos theta. So again, using another identity here. Like so. So, writing that all out now, what we get then for x is that x is equal to a lots of 1 times cos theta, so cos theta, and then cos theta times sin theta over cos theta is just sin theta. Okay. So there we have it, so that's x. And now if we differentiate this, we can set it equal to 0. So dx by d theta, well, differentiate cos theta here, what would you get? Well, that'd be minus sin theta, and if you differentiate sin theta, that'd be cos theta. So this is just a lots of cos theta minus sin theta. Okay. Because essentially what you'd have is a cos theta plus a sin theta, just differentiate both of them individually. And we know this is equal to 0 now. So we just need to work out a. Sorry, not a, we need to work out theta. But we do need a eventually to work out that x quadrant there. So what we can do is we can write this as a 1 minus tan theta. Okay, if you think about dividing both through here by cos theta. So this is a, cos theta divided by cos theta is 1, minus sin theta over cos theta is just tan theta, again using this identity. So this is a bracket 1 minus tan theta is equal to 0. Okay, if you were to multiply through here by a and then just solve, what we would just end up with is that tan theta is equal to 1. So tan theta equal to 1. Nice and easy to solve this. You should be absolutely confident with this. You'll get theta is equal to pi over 4. Okay. So we've got theta. We just need to obtain essentially the x coordinate here now, which is the point. So again, just using substitution here now, r is equal to a 1 plus tan theta. We know tan theta is equal to 1, so essentially r should be equal to a bracket 1 plus 1 here. So r is equal to a times 2 or 2a. So essentially then the point would be 2a and then pi over 4 there. Okay, so that's our final answer there. So I hope that's helped. If there's any mistakes, which there probably is, because this definitely seems to not be my best video, please just let me know down below, or you notice any other issues.